Well, hello there! I hope you're having an amazing day, my dear friend, and that you're ready and excited to learn a lot of new stuff about different types of memory that are being used in our computers, and also the relationship that our CPU has with each of these memory types. So, in order to become an amazing developer, I feel like understanding how memory works is going to be very beneficial. So, if you are going to join me today, I highly recommend you to prepare a very strong cup of coffee, and yeah, let's get right into it. Okay, let's start our discussion today by stating the obvious. Our computers are able to utilize more than a single type of memory, which allows them to actually be able to use different types of memory for different occasions and different situations, based on the fact that each memory has its own quirks, so to say. But when you combine all of these different memory types, you get some interesting results and some great capabilities that we have at our disposal with today's computers. So today we will be talking about most significant and most commonly used memory types that we are utilizing every day without even knowing it while working with our computers. So I hope this sounds interesting to you and that you're eager to learn a lot more about it. Because the information you're about to ingest into your memory is going to have a significant impact on your performance as a developer. Basically, what I'm saying is, not all memory is created equal. So before we get to practical examples, so to say, of which memory is used in which situation, I would like to give you a brief general overview about advantages and disadvantages of each memory type. So you would basically know what to expect from each of those, and that you can make good decisions in which situation you wish to use a specific type of memory, because it definitely can make a lot of difference in certain situations. Okay, so the first type of memory that we're going to discuss right now are going to be registers. So registers are basically the fastest memory we have at our disposal, but it comes at a cost. The capacity that these registers have, so basically the amount of storage they can give us, is so abysmally small that we can only fit a single instruction or a single piece of data inside of them. So we are talking about bytes of memory, not kilobytes, not megabytes, not gigabytes. We're talking about bytes of memory. So they're extremely small, but they're extremely fast because their speed almost matches the speed of our CPU. So basically, the speed at which registers can provide information to our CPU is almost identical to the speed of our CPU being able to manipulate that data it receives. So it is really fast. But why are we then using all other memory types? Why not just use registers if they're so fast? That's a nice point, I agree with you completely. It would really be nice if we could just use the registers as our main go-to memory type. But as I already mentioned, the problem comes from the fact that capacity of this memory type is tiny. We cannot fit a movie or an image or a whole data file or something like that. We cannot do that. It's so tiny, it's so small amount of memory that we can work with when it comes to registers that it's practically unusable for us. But when combined with other types of memory, it is our perfect ally. Our next memory type of the day is going to be cache memory. So cache memory is basically the second fastest type of memory we have at our disposal. So cache memories are located right next to our CPU, so that basically electrons from the current do not have to travel too long of a distance to reach our CPU and send the information to the registers. And after that, our CPU is going to use the data from registers and manipulate it. So basically, in our cache memory, we store the data that might be used next.
Which value might be used next? Are you trying to say that our CPU has some superpowers and can see into the future?
Sadly, no. They cannot see the future and do not have superpowers, but there is one thing that's working for them really well. I'm talking about the algorithms that are being used to decide which data is going to be stored in our cache memory, and the success rate, basically called hit rate, of those algorithms is over 95%. So in more than 95% of the situations, these algorithms are successfully predicting which data is going to be used by our CPU next. So that's a very good prediction, because when you think about it statistically, they should have 50% chance to do it, and they have over 95. So basically the story here is that our CPU really doesn't want to talk with RAM memory directly, because RAM is hundreds, if not thousands of times slower than CPU. It doesn't like talking with it. So basically, that is why we have these algorithms that are going to predict which data is going to be needed, so we can store it in our cache memory from RAM memory, and then our CPU doesn't have to communicate with the RAM directly, so it can pick up the data from the cache memory. I hope I gave a meaningful explanation here, because this topic is really exciting for me and I just keep blabbing on and on about it. So the limiting factor for cache memory is again its size, because in most cases modern CPUs have 3 different types of cache memory, and these memories usually have a few megabytes of storage. So that is not nearly enough to what we are basically using in our day-to-day lives, because we are basically using terabytes of data. So that is why we cannot use it as our main go-to memory type. That is why we actually have the need for our next memory type, and that is RAM. RAM memory is slower than cache memory, but it comes in a much larger sizes. We're talking about gigabytes of memory, and our RAM today is very fast indeed. It was improving over decades in the past, and it has come a long way, so to say. And basically, that is why all the data that our computers are using all the time needs to be loaded in our RAM memory, so it can be available for the rest of the memories, so basically cache and registers and CPU, to be much faster and much more easier to be accessed when compared to its initial state, and that is inside of our hard disk drives or SSDs or NVMEs. So basically, that is why we're using RAM memory. And another very essential topic about RAM memory is the fact that it gets erased as soon as we lose the power. So RAM memory is using transistors inside of it, and those transistors need current all the time in order to save states. So basically, RAM memory again is working with ones and zeros only, and 1 is the presence of power and 0 is absence of power. And if we do not have any power in the entire RAM chip, that means that we only have zeros inside of it. And that is why it cannot save data when our computers are off. Which is why we basically need our next type of memory. And I'm talking about our hard disk drives, which are basically being replaced as we speak by SSDs and NVMe memories. But yeah, when I say HDD or hard disk drives, that is what I'm basically talking about. I'm not talking about just hard disk drives. So this type of memory is the slowest of them all, but it has 2 main things that are working for it and making it an essential part of our computers. The first one is the one that I already mentioned, and that is the fact that it can withstand the loss of power and the data is still going to be there waiting for us and just waiting to be again downloaded into our RAM memory. But also, the capacity of this memory type is substantially higher than the previous ones. So basically here we're talking about terabytes of data. So this is basically our go-to storage memory type. We store everything on this memory type, and it just gets loaded into RAM when we need it. Now, I know that was a whole bunch of talk about different memory types, but I had to cover that because I want you guys to understand what are the differences and what are the main traits of each of these memory types, so you would know what you're working with in future. So now I feel like it's a great moment to start talking about the practical usage and use scenarios of each of these memory types. Firstly, I would like to remind you about the memories that we already covered in our previous videos about Rust. So basically, I'm talking about the stack, heap, and static memories. So I'm just going to give you a quick reminder about each of these memories so you do not have to go browsing for other videos. So the first one is stack memory, and that is our main memory type, so to say, because we're just going to be using it for all the primitive data types by default, and we're going to use it also to store pointers inside of it, even though those pointers are going to be pointing to some memory locations on the heap memory, but either way, they are stored on stack. So pointer itself is stored on stack memory. Then we also have the upper mentioned heap memory, which is where we are storing all the reference data types, or the more advanced or compound data types, call it whatever you like. And this memory is a lot less organized when compared to stack memory, which is why it's a bit slower, and yeah, it's being used all the time in our Rust programs. And the third type of memory is our static memory, which is the one that we are generating basically. So I don't know if it's a right term to call it a memory, because basically that is our executable files and all the information that is stored inside of the executable file itself. So when we are defining some constants or something like that, those are going to be stored as static memory. So they're going to become a part of your executable files, and you will not need to access neither stack or heap memory to access those. You will get them right outside of your executable file. Alright, now that we reminded ourselves about the most commonly used memory types in our Rust programs, it's time to start talking about the ones we mentioned earlier. And to do that, I feel like the best way is going to be through an example. I'm going to use a very simple example, but I hope it's going to be a good enough way to present to you in a very simple manner how everything is going to be working in our computers when we do something like this. So have in mind that this is heavily abstracted explanation. It's way more complex in reality, but if we were going into too much detail, this video might last for hundreds of hours, because that is how much complexity is inside of the process of working with our CPU and memory management and organization and everything like that. So this is heavily abstracted explanation. So we're going to be using a very simple example, as I already said. We're going to be using a scenario where we're going to be creating a new text file and writing some text inside of it. And we're going to be using our Rust program to do it. So the first thing that we're going to be doing is actually to create this text file. And to do that, we are going to be saving it on our hard disk drives. And as I already mentioned, I'll be using hard disk as a replacement for both SSDs and NVMEs. I'm talking about the memory that is not going to be erased when we turn off our computers. And because of the fact that we need this text file to remain available to us after the loss of power, we are going to be saving it on our hard disk drives. And when we do that, it's time to step to our next step. And that step is going to be to upload that file into our RAM memory. thus enabling our CPU to have it at its disposal much easier than if it would have to pull it off from the hard disk drive. So basically, because of the fact that our CPU knows that we are running a program that's manipulating that text file, it knows that it should immediately upload that file to RAM memory. And when that is done, our Rust program is able to actually start running itself and to generate the content that's supposed to be uploaded to that file. And for that to happen, we need to be going through each line of our code and then basically uploading each of those statements into our cache memory. And after that, one instruction at a time is going to be uploaded from cache memory to our registers and then executed by our CPU from registers. And when that is going on, the results of that process are again going to be saved in accumulator register, and then from accumulator they're going to be transferred to cache memory, and again from cache memory we are going to be able to update our text file and have the updated version in the RAM memory and save it on our hard disk drives. So that is a basic explanation about the process and organization, how things work behind the curtains in our computers. Again, this is a heavily abstracted explanation and thoroughly simplified, but I want you to have a general image what's happening. So when we know that, I think it's time to end this video. So I hope it was really enjoyable and useful, even though it was probably complex and difficult to swallow, so to say. But the important stuff is it will definitely help you out understand how things are working under the hood, which will enable you again to become a much better developer. So I would like to thank you all for your support in all the previous videos and to say that I'm really grateful for all of your efforts and support, for leaving comments, liking, subscribing and everything, because it really means a lot to both me and the channel. And in our next video, we will be extending on this topic by actually explaining what is the process of allocating and deallocating memory in our Rust programs. So we are continuing with the general topics, so we are still on computer science topics, but we are going to be talking about these general approaches more towards the Rust programming language. So I feel like the next video is going to be really important as well. So that is why I invite you to join me on that video. And there is nothing else to say except I wish you an amazing day, my friend. And until the next video, goodbye.